So I welcome everyone here to the day 3 events of the World Space Week being celebrated by Sir Parshuram Bhau College, Pune. Today we will be having an online talk on the discovery of the oldest radio lobes hidden trapped inside the cluster Able 980 discovered using GMRT by Professor Surajit Paul. I would like to invite Dr. Sandeep Kakade, the teacher coordinator of Science Association, to welcome our chief guest.
Thank you, Aditya, and I welcome the today's chief guest, Dr. Surjit Paul sir, from the Department of Physics, Savitribai Phule, Pune University, Pune. On behalf of Science Association, Sir Parshuram Bhau College, Pune, I welcome you all the participants for joining the talk, and I am sure that we'll be happy to listen this talk since it's a very fruitful and scientific talk. We will listen throughout this session. So I welcome you once again to all of you. And I will say a few words about the Space Week. Science Association, Sir Parshuram Bhau College, Pune, started to organize the World Space Week from this year. We are organizing this event from 7th October 2022 to 10th October 2022. And Dr. Suresh Naik, ISRO group scientist and chairman of International Space Society, has inaugurated this talk. In this talk, we also have inaugurated the Saikata sessions where the informal communication and discussion on the scientific thoughts will be held among the students. Professor K.C. Mohite and Mr. Vitthal Raigaonkar has inaugurated that session yesterday only. Students have prepared 70 posters and 50 models, and that exhibition is ongoing in the audiovisual hall of Sir Parshuram College from last 2 days, and the exhibition is open to all till Monday 3 p.m. On tomorrow Monday at 3 p.m. we have a concluding remark. On tomorrow morning again we have a student talks, and the exhibition is open for you. And once again, now I would like to welcome Dr. Surjit Paul for his talk. Thank you. Thank you very much.
Thank you, sir. I would now request our Vice Principal of Science, Professor Dhananjay Dute, to please speak a few words about Science Association.
Good morning to all. I am very happy to say that, like every year, we are celebrating the Science Association program throughout the year. This year, with the permission of our principal, Dr. Sunil Gaikwad sir, and our Science Association coordinator, Dr. Sandeep Kakade sir, we are celebrating this Science Association with the World Space Week. So today is the third day. I would like to welcome our chief guest, Surjit Paul sir. He is very good speaker. So all of you are welcome again and join the online talk. Thank you very much.
Thank you, sir. I would now invite Professor Praful Kachwe to introduce the speaker for today's talk.
Hello. Now I will. Good afternoon to all. Here now I will introduce to our today's chief guest, Dr. Paul, Dr. Surjit Paul. Here, after doing his master's in physics at Pune University, he, he moved to Rosenberg University, Germany with DFG, doctoral fellowship, and obtained his PhD under DFG International Guidance School, and returned to India as the postdoctoral fellowship at IUCA and received ACRB. He is the youngest scientist fellowship into He received the youngest scientist fellowship in 2012. Later, in 2013, he was awarded as DST Inspire Faculty Award by DST and joined the Pune University Physics faculty. He is an assistant professor of physics at SPPU since 2019 and is currently visiting Raman Research Institute, Bangalore as a visiting scientist. And other rewards and honors, I will say. He has published numerous high impact publications in top international journals, including the Science and Royal Astronomical Society from London journal. Here invited as the reviewer of many top astronomy journals, including the prestigious Nature Astronomy Journal. He received the prestigious SFB Fellowship from Desi, Germany, and was invited the guest professor as Hamburg Observatory, that is Hamburg University, Germany, from 2015 to 2016. He has been invited by National Supercomputing Mission, which will be held by Government of India. As an expert committee member, he was the coordinator of Saruka Japan Asia student exchange program from 2015 to 2019. He is an associate member of the Science Working Group of Square Kilometer Array World Body. He is also the Vice Chancellor nominated for coordinator of SPPU as Square Kilometer Array India since 2018, a body that is overseeing Indian contribution to the effort of making the world's largest telescope called as Square Kilometer Array. This, this is all about you. Thank you. And great ahead to Dr. Surjit. Thank you.
Thank you, sir. Now, I'm sure everyone here has been waiting for the talk that Professor Surajit Paul is here to give. I would like to invite Professor to please continue. Go ahead with the talk. Thank you all, and we are all eager to listen to it.
Okay, shall I start? Yeah. So thank you, Aditya, and I would like to thank Dr. Sandeep, who is also my friend, to invite in this great event of World Space Week. And also, Professor, I would like to thank Professor Prafull for introducing me. Today, as the title suggests, you can see that I will talk about a discovery made using our own telescope, GMRT, Giant Microwave Radio Telescope. Usually, I like to give such talk in person so that I can interact with the students, closely. But since unfortunately I am now in Bangalore in Raman Research Institute, so could not come for this event, giving the talk in the offline mode. But anyway, I will try my best to give a comprehensive talk online itself. So my talk will start with introduction to some of the basic astronomy, considering that today's audience includes many of the students who are not very well versed with astronomical systems. That's why I will try to introduce it so that they get to know what is all the astronomy about, and mostly related to the discovery that I will be presenting, so that they can easily understand what the discovery is and why it is so important. And at the same time, they can connect their curriculum to the research work that we have done in this. And then I will talk about my research group very briefly, so that people come to know that how this group work, teamwork actually needed for doing such breakthrough research. And thereafter I will come to the discovery, explaining the discovery and all details of that. So as you see on the screen, I hope most of you guessed what is this object is. This is our own sun, the nearest self energetic object. And you can see the great details of this star because of the available facilities, very good facilities that are available nowadays. If you want to understand that how sun is, you see I have given some small information about the star. So you see that the weight or whatever mass is 10 to the 30 kg. You can understand how massive it is. And the size is around 1.4 million kilometers. But this is not a very great or big object when you consider the universe, or even not universe, when you consider our own galaxy. So as we know that our solar system is comprising of some of the planets and comets and gaseous stuffs in between around, and all these are moving around the sun. If you think about our own galaxy, which is known as Milky Way, or we call it Chayapath or Akashganga in different languages in India. If you consider that this whole object is our galaxy, Milky Way galaxy. This is a artist impression, not a real thing, but almost in the scale. In that scale, you will see that solar system is so tiny. I mean, it's not even the sun. Solar system is much larger than the sun. So when I talked about the sun, it was looking a big object. Now you see that overall whole solar system within our galaxy is so tiny. And this solar system is residing in one of the arm of this galaxy. Our galaxy is a special kind of galaxy which is called spiral galaxy. Why? Because it has various arms, like spiraling arms. So this kind of galaxy is called spiral galaxies. And in one of that arm, only a tiny space is occupied by our solar system. Actually, these kind of galaxies comprising of almost 10 to the power 10 to 11 sun. Okay, so you can understand how big it is. And now the size and mass wise, these galaxies are almost 10 to the 12, that is trillion time of mass of sun. And size is 10 to the 5 light years. Light years is nothing but 1 light year is 3.26 solar light 3.26 sorry, one light year, you know that in 1 year the how much that light travels, fine. and this size of this object is about 10 to the power 5 light years. Okay, so you can understand how big it is. And now, if you see our own galaxy from Earth, it looks like this. As I told you, that our solar system is on one of the arm. So from solar system, you will see the disk shape of the galaxy. It's like that. This is a disk, and this side is bigger because we are looking at it from the front face. But if we look on the side face from where we are living, it looks like a uh, disk. Fine. And it feels all over the sky because this object is very big near to us. Fine. So that one was one of the kind of galaxies called spiral galaxy, as I already told you. There are various other kinds of galaxies. The one which is older and comprise only gaseous medium, no star, almost no star, and no arms like spiral one, and shape is elliptical. These kind of objects are bigger than spiral galaxies, much massive. I will come to this one because this will actually make our case in further discussion. So I will come to that later on. But you understand that this is a gas ball, elliptical shaped gas ball of a very massive one, and size is bigger than spiral galaxies. And there are another kind of galaxy which is irregular galaxy, not having very good shape. Those are little smaller than the other two. These are the major varieties. There are sub varieties also. Now you saw that a galaxy is so big. Now I will show you that this is a patch of our sky. If you look through our sky, so let's say we are here in the center. I hope you are able to see the pointer. So if we are sitting here, we are looking through the sky, and our sky looks like this. And in this image, each of the point is actually a galaxy. Each of the point, you can now understand how big our universe is. This is just a patch of our universe. Also in depth, it is very small depth, only in redshift, which is a concept in cosmology, that says about the distance in time. I mean, time and distance both can be computed from redshift information. I don't know whether few of you are aware of how universe was formed. So Big Bang, everyone may be knowing. So at the time of Big Bang, what happens, that each of the point started going away from each one, and that thing continues, and still it is continuing. And because of that, when we recede from one another, that recede distance is calculated through redshift. And that's how you can be here, because I'm looking from here and we can see the depth of the sky. And on the other hand, we are seeing the spatial distance on the sky. It has been on the array, we call it array, right ascension and declination. That has been compressed into one dimension and showing the distance. But the same image, if we see on the sky, which is array, right ascension and declination, it's similar to our longitude and latitude on the sky in 3D geometry. And there you can see that the sky is looking like this. Why I'm showing it? Again, you can see that each of the point here is galaxy, and those galaxies are not placed very randomly. Is it a random? You can see it is not random. There are structures. Like here also you can see structures. Here also. What are kind of structures? There are filaments, there are nodes, all kind of things. And that means when there is node, there the gravity is very much, and it is pulling huge mass into it and forming some structures which we call galaxy clusters. As you have seen in the title of the talk, that one we see the emission which has been trapped inside a galaxy cluster able 980. So those galaxy clusters are residing in the node of these filaments. And again, this is a very small patch of the sky, and there are much bigger sky patches in which actually comprise our universe. Okay, so this is one of the simulation that we performed in our lab only. This is one of the highest resolution simulation available, and you can see that how structures are forming from the initial stage. And each of these, the denser region is where the more galaxies are there, and these circles are telling about the structures like galaxy cluster groups and all, where you have thousands of galaxies. As I told you, that elliptical galaxy I showed, spiral galaxy I showed, each of these node actually comprising of thousands of galaxies. So how big they are, and you can understand the energetics that is this kind of object follows. And another thing you can see is that there are filamentary structures where smaller groups are forming. Fine, these are very interesting objects, I will explain them later on. And this is how your whole universe structures are embedded. All the galaxies and all are embedded like this. And galaxies can be, as I told, that these structures are formed by galaxies. So galaxies can be here in the filament, in the node, in the smaller node, everywhere. So after understanding the structures in the universe, we will move into that what makes them visible to us, right? We can see stars in the night sky, and in day's sky we see our sun, one star, but in the night sky we see many stars, even galaxies and galaxy clusters. So we determine or detect them or understand them through their spectroscopy, which I'm not explaining here very much, but we can actually differentiate which one is star and which one is galaxy and all this stuff, looking at their spectrum. So this is an optical image of a galaxy. This is one galaxy. Okay, so thus in the center, and this galaxy is a big one, and it's a uh, elliptical galaxy. Fine. So this thing we see in the optical. I mean, this is an optical view as taken from NASA. So this is optical view of one cluster, Hercules A. Now, what are the source of optical emission? So, I mean, many students will immediately say that, okay, it is the electronic spectra, correct? And there are black body radiation as well, because these are hot body. So black body radiation forms the profile, and this spectra emission and sometimes absorption when we so this is how the optical emission is happening in these sources. Now the same source, you see, the same source when we see in radio waves, they are forming such a big balloon like emissions. How they form, I will come to that in later stage. But you see that same object which was optically seen such small, in radio it is seen such a big structure. How radio emission happens? I hope many of you have heard about the synchrotron emission. So when electron moves inside magnetic field, it its path gets curved, and this curvature creates acceleration or deceleration from which it radiates, and that is called the synchrotron radiation. The synchrotron radiation produce such radio emission from these sources because there is a huge amount of magnetic field and high energy particles. The same object, now you can see in pink or magenta color, this central part, same object. This is X-ray, again from NASA Chandra Observatory. We have taken this, and you can see that X-ray is giving a different look of the same object. So you have seen the optical in the center, you have seen the radio, and now you have seen all three together plotted, and X-ray is in the center, but in a much wider region. And you know that what are the mechanism of emission, this X-ray. Many of you may be knowing it is called Bremsstrahlung, that is breaking radiation. When it happens, when some electron is moving very near to a big nucleus, it gets, it path gets broken. That is, it curves and it radiates. It's a normal X-ray emission, which you have read in your curriculum in your physics classes. Okay, the same kind of things happening. Obviously, there you see in laboratory in much smaller scale. Here you have a huge volume of high temperature gas, and there you have energetic electrons, which are, when interacting with the nucleus of various material, it produces synchrotron emission, Bremsstrahlung emission. And Bremsstrahlung emission is continuum emission, so you get a continuum emission from this region. So this is how we actually see the objects in the sky, and these are the radiation which make them visible to us. There are other kind of radiations, as you know. Those are like gamma rays, the highest energy, which I have not shown here, but just to introduce the students with various kind of mechanism, I have shown this. Now, how we observe them? Fine, because emission is fine, that is happening on the source, but somehow we have to detect them. But most of our observatories are earth based. At the initial stage it was earth based. So that time we could only see some of the optical things. If you think about the historical observation, all are optical because there is a window in the optical range. So this figure shows you how the our atmosphere is opaque or transparent to different wavelengths. I hope you know that electromagnetic wave are divided into several wave bands. So highest energy wave band is called the gamma rays, where frequency is very high and wavelength is very low. Then X-rays, then ultraviolet, then there is visible range, then infrared, microwave, and the highest wavelength is of radio, which can vary from centimeter to kilometer even. And the opacity of the sky is highest for gamma rays because it does not allow to come gamma ray inside earth atmosphere, otherwise we would have been killed. And X-ray also, and much part of the ultraviolet. For optical we have a little bit of window, and then there are some other lower energy wavelengths, you have some window. Again, the infrared and microwave gets absorbed, but in radio you have a clear sky. So radio can be observed very well from the earth-based systems, earth-based telescopes. One of that is our GMRT. Fine. And the other wavelengths which are blocked, for them what we have done, we have sent the telescopes on satellites. Okay, like X-ray, gamma ray telescopes. like infrared telescopes, those are on the sky. And as I told you that we have a great telescope called GMRT, which is one of the three largest telescope in the world, and it is unique because it can operate in a frequency in which there is no other telescope operating. So those are the low frequencies, and radio astronomy is very interesting in low frequency. Okay, so GMRT can operate between 100 to 1500 megahertz, and the geometry shape of the geometry is like this. So many of you have maybe visited geometry. If you have not, you should visit. So there are 30 antennas, each of 45-meter diameter, and they are placed within a radius of almost 26 kilometers. Why such a big, and why so many? Hmm. Uh, I think you have some understanding about the resolution. The resolution is determined by the diffraction pattern, and the FWHM, full width half maxima. If 2 point sources are separated by the FWHM, 2 times HWHM, their peak are separated by that, we call them as resolved. And how the equation is, there is a very simple equation, lambda by d. What is lambda? Lambda is the observing wavelength, and d is the diameter of your telescope. Now, since already we have seen that radio telescopes, radio wavelength is very high, that means to resolve object on the sky, you need a very big telescope, because lambda by d, it's a inversely proportional. So if your diameter is high, then your resolution is good. That's how you have to place them in a big or large distance. However, making a one telescope of that uh, size is not possible. So there is a technique, very good technique called interferometry, through which we can avoid making a big telescope. Instead of, we can put many telescope at proper places and synthesize a big beam which is equivalent to the radius of the uh, largest distance among these telescopes. Okay, so that's how these are made, and we should be proud that we have one of the largest telescope in our backyard in Pune, near Pune. So I introduced this because our discovery is mainly done by this telescope. Now I am coming to the my research group introducing. What we do is we work on computational astrophysics, because astrophysics is such a thing that you don't have any experimental setup for that. It's a big thing. We call any size or distance or time in astronomical meaning a big, and that cannot be fit into lab. So our lab is modeling simulation. So we can do computer simulation using or modeling numerically many theories and get experimental result from that to match with the observations. And the second expertise that we have is radio astronomy. Obviously, we use all the world's largest radio telescopes for our research. We also keep interest in cosmic ray physics, and our team is currently working targeting the square kilometer array, which is the largest radio telescope being built in next 5 to 10 years. And that time we will need huge number of trained astronomers, radio astronomers, to reduce those data and understand the physics of the sky. And I will ask many of the students who are interested in doing research should think about doing radio astronomy, because that is the future I mean, most of the big discoveries will be done in radio astronomy soon. And this is my group. Currently, there are 5 members, 4 PhD students and 1 MSc student. And 2 of the PhD students almost done. They will be soon joining in 2 of the prominent national institute, one in NCRA, TIFR, another in IIA Bangalore. And other 2 are still working on their thesis. And the alumni are now placed various places. So Dr. Mukul Maske, who is in Germany now, Dr. Reju Sam John, who is in New Zealand doing PDF, Venkat Panjabi, who is doing his PhD in Chile, and recently from Ferguson College, this Sai work, she came to do a project with me, and she has been, she got a chance to do a research project as a JRF in IISc Bangalore, and Subham Bhagat, who is now in Germany doing his PhD, who was a project assistant in my lab. Anyway, now coming to the actual discovery. I think you got the initial understanding of the astronomy that you will need to understand further talk. And here you can see I have put a patch of sky. It's a radio survey sky. And all these points are some of or other radio objects. So many people think about when we say that our discovery has been happened, they think it is done randomly, like what I can say, that serendipitously you have got something. That can happen, but it is not so easy. You need actually the understanding of the system in depth, academic guess, or a systematic study. Okay, so for systematic study, you need to understand things in very deep so that you can, um, put a list of probable objects that may be showing interesting features. So you can understand that finding something among the sky and which is showing very good physics or something is not so easy. So what we did is that we our through our computational work, we predict that who are the very interesting objects. So what we have done, as I showed you in the earlier movie, that objects are forming, there could be galaxy groups, clusters in the node, and all this stuff. So we have chosen many mock catalog of galaxy group and clusters, and then computed that how much radio emission or what kind of radio emission we expect from them. And if we observe them through various telescopes like GMRT and the upgraded, which is the current upgraded GMRT and much improved GMRT, and in future square kilometer array, and we put those lines like this, you can see GMRT even can detect many nice objects or interesting objects. UGMRT will be obviously do better, and square kilometer will do marvel. I mean, it will almost cover all the objects that we want to see. With this motivation, what we have done, we have seen that low mass clusters are very much interesting. There are other reasons which I am not specifying here, but you will slowly understand, and if you further inquire, you will see that low mass objects are very interesting. However, because you can see that geometry cannot detect much of the low mass objects, uh, the same is with other telescope worldwide. So what happened, people used to think that these are very these are not interesting objects, or at least cannot be detected through these telescopes. But my prediction shows they can be. And when I presented this work a few years back, 2015, in a conference in Italy, uh, they told it's not feasible. I mean, they were very much skeptic about the work and all, but that gave me a strong motivation. And what we have done in our group is we have shortlisted many such objects from a list of objects, or list of galaxy clusters available, the best available galaxy cluster list. From that we have chosen a portion of the object with some mass and in the near redshift, so that we can see them well. Okay, so there are other criteria we have set, and then systematically studied them, because our prediction shows these kind of objects are very interesting. So among them, the current discovery was, okay, so what we discovered is this one. This is in radio telescope in GMRT. We have seen this one. This in the sky, one object has been seen like this, and you can understand nothing from this. I mean, radio astronomer would say something, but general population cannot actually think that what is this. But just few 10-15 minutes back, I have shown you that a galaxy can emit radio waves like balloons. If you remember that at the almost at the beginning, while I was explaining about the emission mechanisms, there I have shown. So this is one such balloons. Okay, so you see, this is one balloon, this is one balloon, and below there are two small balloons. So this gives an idea to an astronomer that there must be some big galaxy which is emitting this. Okay, but then also what happens? I mean, you discovered some, these are called radio lobes. I will come to that. But you have discovered what speciality in this. There may be many in the sky. One speciality is this, that this object is trapped within a galaxy. So these contours are X-ray contours. As I have shown that X-ray emission comes from the central hot material, here the galaxy cluster is shown as the X-ray emission. I cannot make it in color because already a color has been put. So what I have done, I have put a contour. These contours are like, the outer contour shows low emission. As we come inside, the contours are at higher emission. Fine. That means this is the brightest region, then slowly faint region. But overall, this is showing a cluster emission in X-rays. And radio waves shows that it has been trapped within the cluster. Now, as I told that the galaxy should be at the center, as I shown earlier, of the emission. But if you see in this image, this big this is the same in contour, radio waves in contour. You can understand, this is one and this is one. Same has been shown as contours in radio. There are other wavelengths also. I am not going into that. But you can see that these are the radio emissions, and we should expect a very bright source, optical source here, which we cannot see in this object. The smaller source cannot be the host of these big radio bubbles. So there should have been one. That big one we see here, much drifted from the center. And another radio bubbles are there. Whether they are connected or not, that I will explain later. But you can see that these two radio bubbles, they have no host in the center. Now coming to radio emission from galaxies, I am coming back because many of you may not have understood that first picture that I showed about the radio emission. So I will go into details of how the radio galaxies are formed, or the lobes or the balloon that I am talking about, they form. So you can see this is one kind of radio galaxy. So you have the central galaxy, and you can see some channels are there going this side, and there is some bright region, and as a whole the plasma has been spread out here, or the radio emitting material has been spread out here, and same on the other side. Fine. So there are various kind of radio galaxies. Some have these lobes, some does not have these lobes. This depends on how they are forming. Okay, so these are various kind of radio galaxies, but what we are interested in, galaxies which are having jets and lobes. Okay, so hotspot you leave it now, but you can understand that. Have you seen this when uh, lorry is going and it is releasing very dark gases? First it comes very comes out of the nozzle very fast, so it is very laminar flow, and after coming to some distance it gets diffused out, right? So you see that, and similar thing happens when you see on the sky some jet plane is moving. You see that very narrow channel like things near to the jet plane, but you see the white gas is spread out when you see little far from the jet plane. So the same thing is happening here. There is a jet and it gets diffused out after moving to some distance, because it is interacting dense medium there. Okay, so fine, but how this jet forms? Now comes that elliptical galaxy. I told you that there are elliptical galaxy which is gas filled, and they are very interesting because they are massive most galaxies. And as you know, I think many of you know that what is black hole is. So a star gets collapsed because of its own gravity. And it gets so collapsed that no information can come out from that. So that is black hole, because the density is so high the light cannot come out. Fine. The same kind of star, that kind of black hole we call stellar black hole. But these stars are residing in galaxies, so there will be many places where these black holes are getting merged and moving towards the center of the galaxy, because center of the galaxy has the potential well, the depth of the potential well is very high, so all heavy materials will move into the center. And because the elliptical galaxy is massive most or very big, they comprise of the largest black holes, which is called supermassive black holes. And such black hole, what it does, it start pulling material from all around, creates a very energetic disk like this. So material is spiraling and falling into the center very fast, almost at the speed of light. The material is moving and going into the center. So what happens, as I wrote, that rapid mass accretion forms the disk. And because this is happening, what will happen is that I have shown a model. You can see that material is moving inside, and since this material is very high energetic, that means there will be charged particles and there will be electromagnetic waves. So magnetic field will be there, and those magnetic field get twisted because it is rotating. So they get twisted, and on the both side of the disc it will form a nozzle, that twisting. And this is one of the model. I'm not saying that this is the whole explanation of jet formation, but this is one of the model which says that this magnetic field get twisted and creates a nozzle, and it then the material that is accreting, instead of going inside the black hole, will follow this path, because those are charged particles. They will follow the magnetic field path and throw them at a speed of light almost. So this is creating the magnetic field twisting, creating the nozzle. Through that, material is thrown out. And if that is happening in a cluster, a galaxy, that will form a jet. And as I told, that jet will move some distance, but then interact with the outer dense medium and get spread out and form the balloon or the radio lobes. Okay, so there can be various kind of galaxies, radio galaxies. Some may not even emit. Why we don't know? Some may be in a non-emitting phase. Later on, that will emit. That is also not known, but it is happening and research is going on. But when they emit, they create this kind of jet, and there could be other kind of bigger jets, which is not that I mean energetic. It will start spreading out immediately, and these are very energetic, and that will flow like a nozzle and create a low. Now, once this happens, that jet emission, this is not like one radio galaxy cannot be a radio galaxy forever. Okay, so it can stop, because when material feeding is stopped, it can lose its energy to, I mean, make jet emissions. So it will stop emitting. There can be some of them which again accretes material if many companion galaxies are available around, or material is available. It will again accrete and start throwing material like jet. So there is example of episodic AGN, active galactic nuclear activity, and in some case it may just stop once, start and then stop. If stops, that means those radio bubbles or balloons are not fed afterwards, because it has stopped. So jet is not feeding them. That means now whatever electrons or high energetic particles has already been thrown inside the bubble, that will start dying out, because they will radiate. Those are very high energetic particles, so they will be radiating and losing energy. What we see that once this jet emission stops, these radio bubbles lose energy very fast, because these are non-thermal energy and they lose energy very fast through synchrotron and inverse Compton. I hope Compton emission you know. So inverse Compton is the opposite of that. Here, the electrons are upscattered by the photon from cosmic microwave background. Fine. So anyway, it loses energy, and then as it loses energy, that means slowly it becomes invisible. Because no energy is emitted, so it will be invisible. And we see that after stopping of jet emission, such thing happens only for tens of millions of years. I mean, for our scale it is big, but in the scale of cosmology, it is very small, tiny time that it will lose. And once it lose, I have shown you one example that they are almost invisible. They become almost invisible. And as I showed you, that this part shows the this is active emission, and this is when it becomes dying or dead. Huh? What happens? The spectrum of the source becomes very steep and even curved. Huh? So that is the actually signal of jet emission. And age of 100 million years, which we have made this graph or this plot. Here we have shown that how the age is varying. Okay, so you can see that age of these outer lobes are more than 200 years. At highest point, it is 260 million years. 200, not 200 years, 260 million years. So before our discovery, the known most old radio galaxy was of less than 100 million years. And we have discovered radio emission which is dying yet seen through our telescope, radio telescope like GMRT. But those electrons that are emitting these radio waves are having age 260 million years. Why it is important? One is obviously that you have found the oldest radio plasma. The other thing is that means now we will be able to study the jet evolution for the longest period of time, because there are many indicators through which we can understand how this jet was formed and how that has been evolved in time. Okay, so those kind of studies now will be done at a much larger time period, which may reveal many new physics in future. So we also tried to explain why this object uniquely showing such a old aged radioplasma. When we analyzed it, because another thing I told you that each of the emission has different physics, right? At the beginning, when I was talking about the emission mechanisms, optical from electronic or this black body radiation, X-ray from Bremsstrahlung, radio from synchrotron. That means each of them are showing different mechanism. So each of them can give you a different clue to the system. So we tried now understanding the system using the X-ray emission. Okay. So as I showed you earlier, this is envelope is of X-ray. Since these are the lobes that we see having so high age, what we have done, we have studied that whether they are confined within something. So what we discovered is that these objects are confined within two cold fronts. And this is another thing in X-ray astronomy done, that when the inside plasma is cold and outside plasma is hot, at the interacting surface there is this cold fronts are formed. That means this outer gas are usually denser and hotter, which is which has kept confined the lighter gas, which is non-thermal radio gas, inside this system. We see both of them showing such thing. And this cluster itself is a cool core cluster. That means which is an indicator of the cluster being relaxed. So a relaxed cluster. And another thing I already told that we have chosen low mass. So what happens in low mass cluster, activity is less. So what happens that it can cool down through red X-ray emission and form a cool core, that is denser core, and outer region remains very hot in this system. So outer X-ray gas is very hot, but inside it is cold, and also this non-thermal emission that is happening in the lobes are confined within such a hot and dense gas. And we explained that because it is confined within such a dense gas, uh, it remains alive because it always have some interaction with the surrounding, and it cannot cool down as faster or cannot lose energy as faster as something which is freely expanding. Fine. We have seen that it is not really thermodynamics, that we can explain it through thermodynamics because we have non-thermal gas. But usually, if you compress something, it remains hot, right? The same thing is happening here. It is happening in the other sense, that it is because of the confinement, the particle loses energy, I mean losing get prolonged, and it remains visible. This is non-thermal emission I am talking about. And as we expected, the temperature of the outer gas is very high. You can see these are the temperature numbers, keV in kilo electron volt. In Kelvin, it is 10 to the power 7 to 8 Kelvin, 10 to the power 8 Kelvin actually, and more. Few times 10 to the 8 Kelvin is the temperature of the gas, which is confining this to radio emitting gas. And that is because of this has remained alive for so long. Another surprise this object is giving. From the beginning, I have shown that there are two different set of lobes, right? I have drawn some red circle here and some cyan circle here to show. And we have shown that I am going back to one image so that I'm sorry. This one. You can see this is one double. We call them radio double because two dumbbell like thing are there. So two bubbles. So these are double, and this is one older double, and this is one newer double. Okay, and now you see that I told you that there is no host here, but here this double has one host. These are the older one, and these are the newer one. This gives a new story into this discovery. What is that? That you can see this new event or new AGN activity has been in the center of the cluster, right? This is the brightest region I told you. So this is the center of the cluster, and these are something which is outside the center. So story becomes like this, that this optical object was actually here a few 100 million years back, and it was in its earlier active phase thrown the jets and formed these bubbles. And because the gravity center is here, at the later time when it stopped emitting radio jets, has moved towards the center. And once it's moved, as I told you that many of the galaxy actually have recurring activities, that same cluster has started new activity. And I'm showing another object. This is called double double because you have the old double, the same host, which is here, actually emitted jet emission at long before, and then stopped and again restarted activity. Fine. So one double, this is older double, and this is newer double. The best thing is that so far people has found only objects which has collinear activities, like the host is always here. And at the earlier stage it has thrown these jets, produce these bubbles, and in a near time again it has activated its jets and produce another double. Before us, no one has seen so distinctly separated two events from the same galaxy or same host. So we report in another paper that this is the clear case of a detached double double. That means the host has been detached or made the earlier lobes orphaned the earlier lobes, and because we call them parent, so it has been orphaned and came to the center and produced new child or new radioactivity. So this is another first from this system. So first time we have detected a system which has detached double double radio emissions. And this could happen because this cluster was relaxed. I think you can understand that if it is not relaxed because of the merger, this galaxy may have moved somewhere, not to the center, because like many objects are interacting with each other, so they will be thrown here and there. But this did not happen because this is a relaxed one. And as I told, such kind of thing in low mass system is very common. So this has become because of the low mass galaxy cluster that we have shortlisted systematically to choose or get very unique uh, emissions from these sources. So this ends the story of this object. Obviously, there are other studies may happen in future with the same object, but our study ends here at this moment. And now as I told that there is two summary, distinct summary from this whole talk. That is, apart from my initial introduction to the astronomy, is that we discovered the oldest radio lobes or remnant lobes we call, with record age of 260 million years. And we discovered the first evidence of detached double double radio galaxy in these studies. So this was one of the important or breakthrough research in this field using GMRT. So definitely NCRA has press released it, and many of the national and even international media, print media or online media has taken it up, like Australia Today. They have published this news in their online version, and also some interviews has been published because of this important discovery, as you have seen throughout my talk. So thank you very much for the attention, and if the channel will be open for question, then I will be happy to answer them.
Thank you so much, sir, for such an amazing talk. And yes, we do have some questions by the students that we have collected, and I'd like to ask them, and I hope you can guide us on them. The first one is, uh, we've been asked, why does other radio waves on Earth, like we use for communication, do not
Hmm.
affect our observations when we study radio waves coming from outer space?
Yeah. So thing is that when we are studying these radio waves, we study them as a continuum usually, and that is in a wider band, radio bands. I will just come to that initial figure so that you can, this one, sorry. So you can see that radio waves is the band is very large, right, here or here. And these communication bands are narrower, shorter, in between they come. Okay, so that actually creates problem to our observation, but we have to throw those data out. Huh? And near to GMRT, always there is some GMRT or any other radio telescope arrays. Government put some restrictions on some bands, uh, uh, which are in the observing bands. But when we made it wide band, these terrestrial radio emission do create problem, but we throw them out and use the rest of the band for our studies. So that's how we manage.
Thank you, sir, for that great explanation. I'm sure the doubt of that person has been cleared who's listening right now. We also have one more question related to your research. Can you
Yeah.
tell us what kind of clusters are the able clusters? So we have been asked, are they open clusters or closed clusters, or are they a completely new classification class?
No, no. This is uh, open and closed clusters, those are in star clusters, not galaxy clusters. Okay, so star also creates some clustering. So these are not star clusters, these are galaxy clusters. So galaxy clusters are of I mean massive, as I told you, 10 to the power 13 to 15 solar mass objects, and they are gravitationally bound. Okay, usually they are gravitationally bound, and that's how they form the X-ray envelope among, I mean, in their medium. And the other question was that what was the last part of the question? Sorry.
So they just asked whether they are open or closed or a completely new classification.
Okay, Abel classification. So
Yeah.
Abel classification is obviously different than the star classification, as I told already. So Abel,
Hmm.
what he did, he took all the galaxies in some region, and there is something called the color diagram. From that, if some, this is a very good phenomena, that if some elliptical galaxies are forming a cluster because they are actually harboring within a cluster medium, they produce similar kind of um, these emissions. And if you do color diagram, means magnitude of, let's say, red and yellow, red and blue, and if you take the difference and plot in the redshift plane, they form a ridge. And from that ridge you can collect all the galaxies. I mean, what Abel has done, he has collected all those galaxies and called them as a cluster. And later on, when the instrument become very good, I mean sensitive, we found that most of them actually showing X-ray emissions as a cluster emission, and that's how this classification uh, got so big name. I mean, Abel is the one of the best classification of clustering, or listing of clustering, you can say. It's not classification because clusters are clusters. They can be called, a smaller one can be called poor cluster or group, and bigger one is the massive clusters. Okay, but how he detected is like that, with color diagram.
Okay. Thank you, sir. I'm sure the person asking this would have had his doubt cleared as well. The last question that we are going to ask you for today is, can you share some information regarding Seyfert galaxies?
I'm not really working on that field. Okay, because I mean, it's not really my field. So I know what are them, but I cannot give you the information I mean, at the level of research. Uh, Sorry, because my field is galaxy cluster. Since some of the galaxy are embedded in the galaxy clusters, I mean unique galaxies. That's how this has come.
Yes, sir. Thank you for taking this stand and showing us the integrity of research in a certain work. And as we are coming towards the end of this talk, I would like to take this chance to provide an official vote of thanks. You have, in today's talk, given us a detailed and very interesting explanation on what and how we do astronomy in the different bands, especially in the radio bands, and have also told us about how you did the discovery of the oldest radio loops that were trapped inside the cluster of Able 980. Thank you so much, sir, for giving us your valuable time and this valuable information. And I'm very sure that this has motivated the listeners to do research in this certain field and clear the doubts of those who are already pursuing this. On behalf of Science Association of Sir Parshuram Bhau College, I thank you, sir, for honoring our request to give a talk and provide insights on radio astronomical research and for giving us such great insights. Thank you so much, sir.
Thank you. Thank you very much for giving this opportunity to talk to the students and presenting this work. Thank you.
To the listeners, we would be ending the broadcast now. Thank you so much for staying with us. This was a really great session.